So let's start from where we left yesterday. If you remember, let me recap quickly. So yesterday we took a scalar field which we call it chi. It's a quantum scalar field. We put it in the sitter, which is the phase where the p is exactly equal to minus rho. And then we said that when the perturbations are inside the horizon, so the wavelength is smaller than the Hubble radius during inflation, this field behaves like an oscillator. And then when the Hubble radius is smaller than the wavelength, there is a phenomenon of freezing. Okay? All right, so now what we want to do, we want to reproduce this result. Yesterday, if you remember, I was a little bit hand waving. I did not solve the equation of motion. This time, what I want to do is to, in fact, to find this same result, but in a more rigorous way, just to convince you that it's true. And then I will just go on computing characterize the fluctuations. So in order to do that, it is convenient to do a couple of transformations. First of all, I will go to conformal time, which was introduced by Matteo the first exercise session. So I introduced a time d tau, which is equal to dt over a, so the dt of the cosmic time divided by the scale factor, in such a way that I can write down the metric in this following form, a squared of tau, which multiplies minus d tau squared plus dx squared. So I collect the scale factor outside, and it's called conformal, of course, because you see the matrix this time is conformal to Minkowski, even though with this strange time tau. Okay? So now what is during a period of the sitter? How does it go? So we know that a of t goes like e to the h star times t. So that's the behavior. So when you solve this equation, so you say that tau is the integral in dt prime over a dt prime. So let's say t here. Okay, so when you do the integral, of course, you are going to get something like minus 1 over h e to the minus ht plus a constant. Okay, you can always redefine your coordinates in such a way that the constant goes away. So from here, you simply, since this is simply 1 over a, you discover that a of tau during the sitter is minus 1 over h tau. So tau is negative, okay, by convention. The beginning of inflation coincides with tau infinity, and then the end of inflation coincides with tau equals 0, okay, in these coordinates. So you go from a scale factor which is very small when tau is minus infinity to tau equals 0 when a of tau grows. So you see, during this, if I do this kind of transformation, the exponential has become just a simple power law. Okay, so this is the first transformation that I need to do. Then what I can do, I can write down the action of my scalar field. If you remember, the action is S of chi equal to minus 1/2. The minus is because of my convention of the metric. The integral in d for x, the square root of minus g mu nu, times d mu chi, d nu chi. Okay, Now I want to write down this in using my metric, so I'm going to use this metric from now on. So this is equal to -1/2 integral in d tau. So I separate the coordinate just to remind myself that I'm using conformal time, so d tau d free x. Here I have the square root of g. Of course, g is a to the 8. I take the square root is a to the 4. Okay? G mu nu, of course, is diagonal, and it always brings me 1 over a square, because the a square is factorized out, so every term has 1 over a square. And then, of course, I have something like chi dot square minus the grad of chi square, okay? In fact, with the minus sign, because I'm using this convention that I should also put a vector here, because this is a three-dimensional nabla, okay? All right, so now what I do, well, maybe I change a sign here, just to have the usual, more familiar, the kinetic term is positive. So here now I do another transformation. I define my chi of x and t, tau, sorry, equal to another field, sigma of x and tau, divided by, this time by the scale factor. Okay? What is the goal of this transformation? Of course, here you see I want to get rid of this term. So let me also erase this, becomes 2. Okay? What I want to do, I want to get rid of this a square here in order to make the action as close as possible to a field in Minkowski. Okay, so that's the reason why I'm doing these transformations. Also, let me indicate by prime, so chi prime, by definition, in this case, is going to be the derivative of chi with respect to tau. Well, in fact, I should use the partial derivative, okay? So that is, the prime indicates the derivative with respect to the conformal time, where the dot was the derivative with respect to cosmic time. So now what I have a chi prime is equal to sigma prime divided by a minus sigma a prime divided by a square. Okay. Now what I have to do, I have to put this object inside the action. So in fact here, again, sorry, this is a prime by my convention. So now the action becomes s of chi equal to 1/2 the integral in d tau d free x a square, and here I have sigma prime square divided by a square, and now you see why I'm doing this, because of course the a square will cancel. Then I have plus sigma square a prime square divided by a to the 4th minus twice sigma prime sigma divided by a cube times a prime, and then I have minus the gradient of sigma divided by a square. Okay? So you see now I start gaining something about this transformation, because now the a square will go away. So let me rewrite this term in the following way. I have 1/2 integral in d tau d free x. And now I start simplifying. I have sigma prime square minus the grad of sigma square, which is what I wanted. Then I have plus sigma square a prime square divided by a square, because here I have a to the 4th and here a square, minus 2 sigma prime a prime divided by a, and that's it. Okay? So I give you time to copy it. Now what I do, I realize, in fact, that this term here is nothing else. So let's change the blackboard, just not to make a mess. This term here, 2 sigma prime, I write it as the derivative of sigma square. Okay? And I integrate by part. So the term which is minus 2 sigma prime a prime divided by a, when I integrate, so I write it as I said, I write it as minus sigma square prime a prime divided by a square. And now I integrate by part. in the action. So what I will get simply the overall term. Of course, I throw it away. Then this will give me sigma square, and then I have to derive this term, which is a double prime divided by a square minus 2 sigma square a prime square divided by a cube. Okay. All right. So that should wait a sec, because that should cancel the wait a sec. I think I make an error. So this is correct. I integrate by parts, so I get this. And then, no, because there was an a here, sorry, that's the reason why there is no factor of 2 here, and this is square, okay? So that's correct. So you see this term here cancels this term here when I do integrate by part. So what I get at the end, I get an action, which is sigma, S of sigma. So in fact, this is now S of sigma, okay? So S of sigma is equal to 1/2 the integral, and I'm almost done, d tau d free x. And here I have sigma prime square minus the grad of sigma square. And then I'm left with this term here, plus sigma square a double prime divided by a square. Okay, so that's what I have. So my action is this one now. So you see now the action is the action of a scalar field in Minkowski almost, because there is no scale factor here, but with a frequency which is in fact depending upon time. Okay? And what is this frequency? If you say that A is minus 1 over h tau, A prime is equal to 1 over h tau square, A double prime is equal to minus 2 divided by h tau cube. So A double prime divided by A is nothing else than minus 2 divided by h tau cube, which multiplies minus h tau. So you see that there is the minus goes away, the h goes away, and this is nothing else than plus 2 over tau square. Okay? So in principle, what I can do, I can replace this by simply 2 divided by tau square. And you see now the mass is really depending upon time, the mass square, the frequency, if you like, of this oscillator, which is the reason why perturbation will be generated. Okay, so now, since we have the action, what we can do is write down the equation of motion. So you just simply take the Euler-Lagrange equation of motion, which gives me simply the equation of an oscillator, but this time with a mass which depends upon time. So you get sigma double prime minus the Laplacian of sigma minus a double prime divided by a sigma equal to 0. Okay, so that's the equation of motion. Of course, now I do the Fourier transform, and what I get sigma double prime k plus k square sigma k minus, and here I put 2 over tau square sigma k equal to 0. So that's my equation. Okay. And now you see the advantage of doing all these transformations, because you see, suppose now that I compute k over ah. During the sitter, I have k divided by minus 1 over h tau times h. You see? So the h goes away, and I have minus k tau. Remember, the tau is negative, so there must be a minus sign here. Okay, so that is the ratio between the comoving momentum and the comoving Hubble radius. And notice that exactly, you see, they enter in the combination k square and tau square. Okay, so now let's go back to this, I think I can raise here. Let's go back to this picture of the Hubble radius versus the wavelength, because now it really becomes much more clear what is going on. So, suppose that I have a Hubble radius, and again, suppose that the wavelength is much smaller than the Hubble radius. What does it mean? It simply means that K divided by AH is let's say much larger than unity. Okay? But what does it mean? It means it's simply that minus K tau is much larger than unity, and therefore K is much larger than minus 1 over tau. But if you look at the equations, then from there, I can discover that in this case, the equation simplifies to a simple harmonic oscillator. Okay? Because I can neglect the third term compared to the other one. And then the solution, of course, is sigma k of tau, when I'm deep inside the Hubble radius, is simply equal to a e to the minus I k tau, and then by normalization I can put a square root of k, plus p e to the I k tau divided by the square root of k. Okay, it will be just a simple harmonic oscillator with ingoing and outgoing waves. On the other hand, if I am in the opposite direction, so I'm taking this time the wavelength much larger than the Hubble radius, I have k divided by AH much more than unity. So that means minus k tau much more than unity. And therefore, the equation of motion, I go back to that in the box. I have sigma double prime k minus 2 divided by tau square sigma k equal to 0. Okay? Now we remember that in fact I go back that this 2 over tau square is nothing else than a double prime divided by a, so I rewrite it like this because it's convenient. From which I deduce immediately the solution, because of course you notice that I can write down sigma double prime divided by sigma equal to a double prime divided by a in this limit, and therefore I discover that the solution is nothing else than sigma proportional to a, sigma k proportional to a. It goes like a. Okay? But if you remember that we define chi to be sigma over a, we discovered again that the field we started from, the fundamental field, when the perturbations are on super Hubble scales, sigma goes like a, you divide by a, and chi freezes in. Okay? So that is the kind of picture that comes out from these changes of coordinates. We can go a little bit more technical in the sense that now I want to compute, in fact, the full solution exactly, but I have to require some boundary conditions, because now I have you have to specify what is your vacuum, if you like. How do you start? And here I can choose my coefficients A and B. As you, in fact, there is full liberty, full freedom how to choose them. Every time you choose this coefficient deep in the Hubble radius, in the Minkowski limit, you are basically defining your vacuum. Okay, so you say my vacuum at a given instant of time has a given number of properties, and according to the property that you want to impose to your vacuum, you choose the coefficient A and B properly. Now, what people do usually in this business is to define what is called the Bunch-Davies vacuum, or called BD vacuum, which is equivalent to say that I have 0 particle as an initial condition. Okay, so there are no particles at the beginning of inflation. And in any case, if you had some particles, if inflation starts after a few e-folds, this condition will be satisfied. So if you think in terms of quantum field theory, a second quantization, this coincides with assuming that the positive frequencies there term is 0, so you have to impose A equal 1 and B equals 0. Okay, so you neglect this this term here. So you choose only outgoing phases, outgoing waves. Of course, that is just a choice. Some people don't like it, but that is what is coming out from this reasoning, zero particle. So in fact, this condition is the one also that minimizes the energy of the system. You can easily prove that it is true. I'm not going to do it now, but it is in the notes. So this is the choice that I'm going to make. But again, remember that is not the only choice you can make. You change a vacuum, you change your boundary condition, you're going to change this coefficient. But from now on, I will take A equal 1 and B equals 0. Okay? Once I've chosen this, I've made this choice, I can solve the equations exactly, because I know that I want some boundary condition deep in the ultraviolet when I'm very much inside the Hubble radius. I can solve the equation. In fact, you could solve the equation exactly with some hypergeometric function and so on, but I don't want to do it because I want to teach you a technique, a simple technique that in fact you can use sometimes when you don't have such a problem, but you have a problem which is a little bit more complicated. So it's sometimes when you are not able to solve the equations, or Mathematica does not solve it for you. There is a trick that you can do. It's a simple trick, which is the matching, in fact. So let's suppose that you separate your region into stages. You have the Hubble, so you have a region on the left of the Hubble radius and on the right. Here you impose that the solution is 1 over the square root of k e to the minus I k tau, okay? And then you have a wavelength that is going out, so you impose also that k over ah is equal to 1, so the matching, you do it the moment the wavelength goes out of the Hubble radius, okay? That is when you do the matching between two solutions. The other solution, let me call it C of k times A for the sigma. So of course the coefficient of the proportionality will be a function of k, which is just a dumb parameter here. And you do the matching at this point, okay? So what you do, you impose that C of k is basically equal to 1 over the square root of k times e to the minus I k tau at the time at which k over ah is equal to 1. So it's clear that in this case, sorry, there is also an a, of course. So this becomes e to the minus I k tau divided by the square root of k. And then from here, I learned that this is k times h. Okay? So if I want to compute the modulus now, the modulus of C of k, which is the only one that is physical, so the modulus will be simply h over the square root of k to the power 3/2. And in general also there is a factor of 2 that we can do because you want to normalize like a Klein-Gordon scalar field. So let me put also a 2 here because you have the square root of 2 omega usually. So I put a 2 here, just a conventional, and then I get this 2 to the power k over 3/2. Okay. So that is the C that I will need. So what happens is the following. The moment the perturbations of my initial chi-scalar field becomes larger than the Hubble radius, okay, so this is the Hubble radius again, my scalar field chi freezes in with an amplitude which is given by this number here, okay? So that is the amplitude as a function of the, so let me write it down a little bit better because it's important. It's an amplitude, and also it's not I should write down like this, okay? If I want to put the k 3/2 inside. So this is the amplitude of the scalar field chi, free scalar field, the moment the perturbation go out of the Hubble radius. It depends on k, of course, but the amplitude is given by h. Okay, the Hubble rate, which is the only scale, energy scale you have in the problem, in fact. So of course, by dimension arguments, it has to go like this. All right, so now notice that there is this strange power, 3/2. And now I want to show that I want to define what is called the power spectrum of this scalar field. And then we are going to get a fundamental result that is in fact the pillar or all the cosmological perturbations, which is the following. I define, yes. Say it again, sorry. Yes. Here is sub, and here is super. Yes. Yeah, on the K, and the idea is that, I mean, you can do it more properly, you can find the exact solution, but when you go to very large wavelengths, of course the fluctuation does not freeze in exactly at the Hubble crossing. It will freeze in a little bit later, but the asymptotic value is given by this. In fact, you can solve the equation exactly, but this trick is more useful, I find. All right, so now what I can do, suppose that now I have created this perturbation during this de Sitter phase. We have learned that inside the Hubble radius they behave like oscillator, they stretch, and then they become constant in amplitude. And I want to compute the variance of this field, suppose. So the variance, of course, is going to be the integral in d3k divided by 2 pi cube times the modulus of the fluctuation as a function of k modulus square. So that's my definition of the variance. You get it from expanding your field in Fourier space, and then take the, so here, in fact, it should be the vacuum, if you like. And then you use the annihilator and creation operators. This is what you get. Okay? But now what I can do, I can write down this as the integral so I do the integral over the angle because there is no angle dependence here. So I get 4 pi divided by 2 pi cube. And then I get integral in dk k squared times the modulus of chi sub k square. Okay? Now what I do, I write this as the integral in dk over k times k cube divided by 2 pi square, which is this ratio here, times chi sub k square. And I call, that's my definition, I call, this is the power spectrum of my chi field. So I characterize the fluctuation of my scalar field in this way. Okay? And now you know, you see why there is this famous k to the 3/2, because now when I take the square, the k cube will go away, and what I will get simply h over 2 pi square. Okay? So this is really the fundamental result of the cosmological perturbations, which tells you that the power spectrum, defined in this way, which the power spectrum is the only object that in fact you can measure, because of course when you do an experiment you don't measure a single momentum perturbations, you measure of course an ensemble of them. So you need to define a power spectrum. The power spectrum is independent from the scale k, or from the wavelengths. Okay? We said that the power spectrum is flat in that sense. It's flat because it does not depend on, there is no dependence on k. Not only that, but you notice that the amplitude is what is called in this subject the Hawking temperature, which is basically h over 2 pi. Okay? So it goes like the square of the Hubble rate, which is the only energy scale you have in the problem, in fact. So in other words, let me also define another quantity. If in general I define the power spectrum as some amplitude times k over some scale k star to the power n minus 1. So that's my, in general, I can write down the power spectrum as long as it's writable like a power law like this. The quantity n is called, the spectral index. Okay? The spectral index of a simple massless scalar field in the sitter is equal to 1. Okay? So meaning that flat means n equal to 1, which is called also an Harrison-Zeldovich spectrum from by historical reasons. Okay, so that is a fundamental result. So I want to pause a little bit about it because it's really, really the pillar of what I'm going to do also later. A field which is almost massless during inflation or exactly massless has a power spectrum whose amplitude goes like the square of the Hubble rate and is almost independent of the scale, or in this case, extreme case, independent of a scale. Okay, meaning that the spectral index is equal to 1. By convention, you put a minus 1 here in such a way that this is 0. Okay, so having said that, of course, you might say, well, but in fact, we don't live in the sitter because we know that inflation has to stop at some point, right? Yesterday, I introduced this concept of slow roll parameters. I introduced the concept of the epsilon parameter that tells you that when inflation ends, you remember epsilon is very small during inflation. Inflation ends when epsilon is equal to 1. So you might say, well, but this result is only true because you took h equals 0. H equal constant, which is true, in fact. So let's see in an intuitive way how this formula will change when I include also the slow roll of my inflaton field. Okay? How you can do it? You can do it in two ways. You can rewrite, you can redo all the computation that I've done so far, but this time in the scale factor, you have to include the notion that there is a slow roll. So in other words, the scale factor won't be anymore like this. It will be slightly different. It's not a very big difference because the epsilon and the eta parameter, the delta, you remember, are very small. So you have to redo all the computations. You have to recalculate your action, recalculate your equation of motion, and then you will get the result. Okay? It's rather, you can do it, of course, it's just a matter of time. But now what I want to teach you is another method, much faster, to obtain the same result, which I believe is also more intuitive, which is the following. It's a graphical method, and then we will take advantage of it to derive the result. So think about this picture here. If you remember, we plot the log of some scale times the log of A, and we have this period of inflation where here is the radiation and matter dominated. You have a period of inflation, a given wavelength is going out of the Hubble radius, so this is basically the Hubble radius, and here is the given wavelength, okay? And here, let's say that you have inflation. This is the period where you have inflation. So a given wavelength will go out of the Hubble radius at a given time, and then it will stay outside the Hubble radius for a long time, and then it will re-enter much later, okay? Now, we said that the power spectrum is of this sky field is h over 2 pi square. But here, what I want to do, I want to basically introduce also some dependence on the scale. So I want to compute exactly this n minus 1. If I do the sitter exactly, we said that n is equal to 1, so there is no problem. So, but what I want to do, I want to replace this by some amplitude that I don't know what it is. Well, I know that it's going to be very close to this. And then I want to parameterize, as we said before, my power spectrum at n minus 1. Okay? So in general, from this formula, what you get? You get that n minus 1 is the derivative of the log of the power spectrum with respect to the log of k. Okay, in fact, this is the definition of the, if you like, of the spectral index. Whatever power spectrum you have computed, you take the derivative with respect to log of k of the log of the power spectrum. Okay, so if you like, this is a definition. In this case, it's for the chi field that we are interested in. Very well. But now, in this picture, you see that since h dot, if you remember, is equal to minus epsilon h square, h is not exactly constant, right? So what happens is that that's the reason why, even though I didn't draw it very well, but it's not, the line is not exactly constant. There is a kind of steepness, okay? In fact, if you like, I should do like this, because the abort rate is going down a little bit. Well, no, in fact, this is the h to the minus 1, so I was correct, it's like this. Let me exaggerate, okay? Let me do some steepness here. So a given wavelength, so take now another wavelength here that goes out of the abort radius a little bit later in time. He will experience this wavelength, an abort radius which is not exactly the same, the first wavelength when he went out of the abort radius, but a little bit different, because h is changing, but not that much. Okay? So what I can do, I can take now my power spectrum, which I learned like this, and I can write down, in fact, n minus 1. I write it as the derivative of the log of p with respect to t times dt over the log of a times d log of a divided by d log of k. So I rewrite this derivative. I use the chain rule, and I write it like this. So far, I have done nothing. But now, what happens is the following. Since the perturbation they freeze in at the abort crossing, when h is equal to k, this derivative is 1. Okay, because I measure at that point where the wavelength goes out of the abort radius. dt over d log a is nothing else than 1 over h. Okay? And then what is d log of p over dt? Well, I take it from here. It's going to be, you see, the log of p is what? Is twice log of h. Okay, so when I take the derivative with respect to dt, it's going to be, well, let's say derivative with respect to dt is going to be 2 divided by h dot. Okay? And then I have, from here, I have simply h dot divided by h square, which is equal to, with a factor of 2, which is equal to minus 2 epsilon. Okay? So physically what happens is that if I have a given wavelength or a given momentum k1 and k2, in fact the abort radius or the abort rate at which the wavelength goes out of the abort radius, I can write it down as a h of k1 and the h of k2. They are slightly different, and the dependence in k is basically absorbed in the value of h at that momentum, at that value of the abort crossing, and then I take into account in this way. So I discovered that in fact, in the period of, which is not exactly the jitter, but the fact that inflation has to end at some point, that I mean rho roll, the spectral index is not exactly 1, but it is n equal to 1 minus 2 epsilon. So it takes into account the fact that inflation, in fact, is in rho roll. So it's slightly different from 1, a little bit, not that much, but still not equal to 1. Okay? And now you start seeing the effect of the beauty of this picture, because as we will see this morning, in fact, the spectral index of the power spectrum which is measured, which is not this chi field, because so far we said that chi field is a generic field, but we will discover that the spectral index of the perturbation that we want to describe, which is the curvature perturbation, I will introduce it later on, is 0.96, more or less. So it's not exactly 1, but it's smaller than 1. So you see epsilon is positive, you remember, so this guy is always smaller than 1, but only by a small amount. So you start seeing already that this picture makes sense, because this simple picture of a scalar field in the sitter already tells you that the spectral index must not be equal to 1 and must be red, so smaller than 1, not blue, larger than 1. Okay, but only by a small amount. And here we go. This is an observation. It's not a theoretical prediction. Okay, so you already start seeing the things that come into place slowly. Okay. All right. So how much time I have for the first lecture? 10 minutes. Okay. Yeah. So now I want to take advantage of this simple picture to tell you about. So what is the plan now of the lectures? Is to use this building block to, in fact, write down the power spectrum of a quantity that we can observe. Okay, so far the scalar field is a generic scalar field. I didn't give it an identity card, but what I want to do next is to define an observable of which I want to compute the power spectrum, and we are going to use these results from now on. Okay, so that's the reason why this result is so important. But before doing that, I want to take advantage of this simple scalar field, because there are other degrees of freedom that that are also produced during inflation, which are the gravitational waves. Okay, so I want to show now. I want to compute the power spectrum of the tensor modes of the gravitational waves, even though I should not call them gravitational waves, but tensor modes. So spin 2, helicity 2 objects that are produced inevitably during inflation. Okay, so because I want to take advantage of these results, so and also I think Matteo will do an exercise. He will use this what I'm going to teach you now. So again, suppose that I want to compute the fluctuation of the tensor modes, which becomes, of course, I mean, you can think of them as gravitational waves, even though when they are produced, they are not really gravitational waves, only at infinity. Okay. So what is how you define the gravitational wave? So that is, if you have taken, which I'm sure you have, a GR course, those are the fluctuation that has 2 degrees of freedom, because they are transless and trace free. So it's I write the metric in this way. Let me go back to the usual cosmic time. So I have a square of t, and this time, instead of writing dx squared, I have delta ij, and then the fluctuation hij, which are the tensor modes, dxi, dxj. Okay, and sometimes people put a tt to remember that those are traceless and transverse free, but let me not bother about this label here for the time being. So if I now write down the action of these degrees of freedom in the sitter, what I'm going to write is that S of h is 1 over 32 pi g Newton. If I introduce this in the Einstein-Hilbert action, then I have the integral in d for x, square root of minus g, and then I have basically h dot square ij divided by 2 minus the grad of hij square divided by 2. So the action, as you see, at a quadratic level, the 2 degrees of freedom do not talk to each other, because, of course, you know that when we will do the counting of degrees of freedom later on, but for the time being, you know that helicity 2 objects, the gravitational wave, have 2 degrees of freedom, which you call generically h cross and h plus. So there are basically, they behave like 2 scalar fields, okay? Like the chi field, nothing different. They're really the same kind of computation that you have to do. So that's the reason why I'm introducing now. There is also a strange factor here, 32 pi g newton. So that is basically the reduced Planck divided by 4. Okay, so what do you do in order to make it canonically normalized? What you do, you define some Hij divided by 4 or divided by 2 equal to some Vij. So you canonically normalize this, well, also divide by M Planck, of course, if you want. Okay, so to remove the M Planck and to canonically normalize, because you want to reduce this factor of 4 here. You want to get rid of it. So now the action will become basically the action, as you see, the action of two scalar fields, two chi fields, if you like. They evolve independently. So the results that I computed so far, you can apply directly without doing any computation, because we already have done it completely for one scalar field. So the action will be the action of two scalar fields, which are a little bit strangely normalized to get a canonical normalization. So there will be 2 degrees of freedom. So will be the H plus and H cross. Both of them behave like massless scalar fields. In the sitter. Okay, so now you use the same computation that I've done, and what you get the power spectrum of this H of K is going to be what? If I sum up the 2 degrees of freedom, it's going to be 2, because I have 2 degrees of freedom, so this is the 2, times I have a 4, because of course I remember at the end of the day that the canonically normalized field that is Vij, so there is a factor of, you see, there is a factor of 2 that goes into this, since it's a square, because the power spectrum I get a factor of 4, okay? Then what I have H over 2 pi square, correct? And then of course the M Planck square, because of course the H are dimensionless quantity. You see, the way I define them, they are dimensionless quantity. They are just numbers. They don't have dimensions of energy. Okay, so that is the power spectrum of the tensor modes. As simple as that. Yes, because the action is exactly the same. You see. So the spectral index, which is called NT. Okay, for some reason which I never understood, the spectral index this time of the tensor modes is not defined to be n minus 1, but there is an nt only. Okay, so there is not a minus 1, I don't know why, but nt is going to be minus 2 epsilon. Period. Okay? So the power spectrum of the tensor modes produced during inflation is not exactly equal to 1, but has to be read, because this is for sure, we know that this is more than 0. So if one day we will measure perturbations from from large scales that we believe come from some period of close to the Big Bang, and we notice that this perturbation have a spectrum which is blue, so larger than 0, that we are sure there will not come from inflation. Okay, so that's a reason, one way of characterizing the perturbations from tensor modes. These tensor modes, and now I will take a break. It's measuring this spectrum is one of the goal of the future experiments, like this, what is called the stage 4, the CMB. They have not been measured yet, and they will show up in the CMB anisotropy, because what happens is that if there are these tensor modes or gravitational waves during the last scattering surface, when the photons scatter for the last time of the electric charges, the presence of these tensor modes will create a polarization in the CMB. In fact, a B-mode polarization, which has a given pattern in space. So people are trying to measure this polarization in the CMB, in the B mode. The problem, what it is the problem? The problem is that the amplitude of these tensor modes goes like h, and we don't know how large is h, okay? The current experiments, or the future one, will be able to measure the presence of the tensor modes through the polarization of the CMB anisotropy only if this h is large enough, something like 10 to the 14 GeV, corresponding to a scale of energy driving inflation of order of the grand unified theory scale, like 10 to the 15 GeV. The moment the h is a little bit smaller than these numbers, the experiments, even the future one, even the most optimistic one, will not be able to measure it, unfortunately. Okay? But if we are lucky, and if nature has decided to drive inflation at very, very large energies, we will be able to measure. And since this, the power spectrum is flat, it also goes to very large wavelengths, so it has a pattern that will appear on super Hubble scales. That will really be the imprint of of the presence of the fact that the inflation was taking place during the evolution of the universe. So that is the last pillar that we are looking for. Now, then, after the break, I will go back to the scalar perturbations, and I will take you from the prediction to the observation slowly to convince you that, in fact, there are other building blocks that match perfectly with the observations. But I think now we can take a break, and then we'll see you in 10 minutes, I guess. Okay. Can we start? All right. You ready? So now, what I want to do is to build from what we learned so far, add one more ingredient, which is a fundamental one. And what I want to teach you, in fact, the fact that what I've been telling you so far is in fact wrong, okay? And then I will correct myself and get the correct result. And you will understand why I'm saying that. So when we did the exercise for the scalar field, if you noticed, I didn't take any gravity in the business apart from the background. The scale factor was taking care of this de Sitter phase, and everything went very well. But now let's suppose, to go back to the initial picture, and let's suppose that the scalar field that I've been talking about so far is in fact the inflaton field, which is the real driver of inflation. So let's go back to the inflaton field. Okay. And let's suppose that I want to consider perturbation of this scalar field, delta phi. Okay? So by definition, the inflaton field is the scalar field that is driving inflation. So it's the scalar field that gives the largest contribution to the energy momentum tensor during inflation. By definition, if you have many fields in your problem during inflation, you call inflaton the one that is dominating the energy density. It might not be always the same field during the trajectory, but let's suppose you have only one. So under this assumption, there will be a fluctuation of the energy momentum tensor of the scalar field, or in general, of the full energy momentum tensor. But by the equation of motion, you know also by Einstein equations, you know also that this will change the Einstein tensor, because of course the equation of motion from that Einstein taught us tells us that the metric is depending upon the energy momentum tensor. But then of course when I go back, I close this triangle because of course the moment I change the metric, as we have seen from the action, there is a g mu square root of minus g. The perturbation of the metric will also feed back on the perturbation of the phi. Okay? So it is clear that what we have learned so far is only in the case in which the scalar field was not perturbing the energy momentum tensor, and therefore the metric was not perturbed. So in fact, let me also say delta g mu with the g minuscule, the metric. Okay? So what I want to do now is to concentrate on the scalar field and take into account also, because of this picture, of the perturbation of the metric. Because I'm obliged to do it, I cannot neglect them according to this simple reasoning. So let's perturb the metric now. And I do it in the following way. I write down my metric, g mu nu of x and t, as g mu nu of the Freeman-Robertson-Walker, which is only a function of time, of course, plus fluctuations. Okay? And since there are many degrees of freedom in this metric, what I want to do now, I want to offer you a simple computation that tells you how many scalars you have in this metric. Okay? So suppose that you have a space-time of capital D dimensions, which is n plus 1. So n is the number of spatial dimensions, and 1 is time. This n you should not confuse with the spectral index, which is just a label to indicate number of spatial dimensions. Okay? All right, so now, as you know, the metric is symmetric. So how many degrees of freedom I have? I will have 1/2 n plus 2 times n plus 1. Because if you have, remember, if you have x, a symmetric matrix of x cross x, you have x plus 1 divided by 2, but this x is n plus 1, so you add a 1 here. On the other side, we know that in general relativity, we have the freedom to make a coordinate transformation of all the coordinates. So I have the freedom to remove, to do n plus 1 coordinate transformation. So I remove n plus 1 here, because I have the, by transformation, gauge transformation, in fact, coordinate transformation, I can remove n plus 1 degrees of freedom. Okay? So that is the physical degrees of freedom of that are contained in the metric. And now I classify these degrees of freedom into the way they transform under rotations. So I classify the degrees of freedom according to rotation, taking, of course, a slice t equal constant. Okay? So what I will have? I will have scalars, I will have vector perturbations, and I will have tensor, the one that we described just before the break. So I want to compute now how many scalar degrees of freedom I have in my system, in this generic metric. Okay, so I want to extract out of this number how many scalar degrees of freedom I have, how many vectors, and how many tensors. Well, let's start from the tensors, and sorry, from the vector, and then we'll go to the tensor, and then of course the rest will be just the scalars. So you know that in general, if you have a vector, you can write down a vector vi. And notice here I'm using the Latin indices to describe spatial coordinates, so it goes from 1 to n, because I'm taking a slice t equal constant. Any vector, according to the Helmholtz theorem, can be written down as the gradient of a scalar plus, let me call it xi, okay, some other vector, such that the gradient of x is equal to 0. Okay, so what I discover from here is that the number of vectors, in fact, is n, because I goes from 1 to n, minus 1, because I impose one condition. So I have to remove from here if I want the number of scalars, so this is the number of scalars, I get this number, I remove n minus 1. Okay, now I have to remove the tensors. The tensor, of course, they belong, as you know, to the, I have if you start from the matrix n times n, how many degrees of freedom in general of that sub-matrix? 1/2 n plus 1 times n, okay? Then, of course, you have to impose the condition that you want to say that the tensor are traceless and transverse, so you remove the 1 from the traceless condition, okay? And then, of course, the other condition is that you remove also the, okay, so this is traceless, minus, you remove also the n minus 1 from the transverse free. Okay. So what you have to do at the end of the day, no, sorry, not minus 1, n, of course, because there are n conditions. So you take this number now, and you take it out from this. So let me put minus the square. Okay, if you do the computation at the end, you get 2. So inside this metric, in general, in n plus 1 dimensions, there are always 2 objects that transforms like scalars under rotation. Okay, those are called gravitational potentials. Well, it depends where they are sitting in the metric. Of course, in the metric, you can put them wherever you want. You can put in the entry 0, 0, so time, time. You can put them anywhere. It depends on the coordinate choice you choose. But in general, there are only 2 degrees of freedom under rotations. And now I want to focus on those. Why? Because the scalar field phi is a scalar. So I want to see how the scalars, at linear perturbation theory, of the phi mixes with these 2 scalars. Okay? So this is information number 1. So for instance, there is, let me give you one example. It's not the only one. In fact, there is an infinite number of choices that you can do where to put your scalars. But in general, I can choose the Newtonian gauge, where I can put my coordinate, my 2 scalars in this way. I have minus dt square, 1 plus 2 phi. Let me put a capital phi not to be confused with the scalar field, plus a square of t, 1 minus 2 psi times dx square. Okay? So, for instance, the Newtonian gauge, which is the one that you use in Newtonian physics, so when you are basically not on super Hubble scale, but sub-Hubble scales, you introduce these 2 scalars, the lapse function and the gravitational potential, that parameterizes these 2 scalar degrees of freedom that I have in the metric. Yes. Yes. The total number of degrees of freedom that I have in the metric, I remove n plus 1 because I can do n plus 1 transformations of my coordinates. I remove the vectors, I remove the degrees of freedom of the tensors, and the answer is 2. Of the scalars, yes. So the remaining are scalars. All right. So now, so for instance, this is a gauge choice. It's a coordinate it's a coordinate choice. It's not the only one, of course, but it's the one that we will be using so far. So in the following, sorry. Okay. Okay, so now that is, so remember, how many degrees of freedom scalar you have in your problem? You have 3, because you have 2 from the metric and the inflaton field. And now I want to see how they mix in such a way to derive something which is physical, some observable that is physical. Okay, so now let me now tell you why what I told you so far is wrong. And the reason is because, in fact, the reason is a fundamental reason, is the reason that GR is a gauge theory, where the gauge transformation are the diffeomorphism, are the transformation of the coordinates. Okay? So it's clear that if you want to write down something which makes sense, like anything else in physics, you have to define an observable, something that does not depend on the observer, something that is independent of your coordinate choice, okay? So let me show you, in fact, that the computation that I've done, to some extent, is incorrect because it does not take into account of a simple statement. Let's consider a scalar quantity. Let me do the exercise for a scalar quantity. Let me call it f. Okay, f of x and t. In fact, from now on, I will use, instead of t, I will use x0 just to uniformize using the coordinate x mu. So let me put t equal to x0. So by definition, what is a scalar? A scalar is a quantity that if I change my coordinate and I go from x mu to x tilde mu, a scalar is a quantity that transforms in this way. F tilde of x tilde mu is equal to f of x mu. Right? This is what you know. This is something that we learn in special relativity already. So, but now, so you can think of it as my scalar field, the inflaton field, for instance. The inflaton field is a scalar, so it satisfies this rule. But I want to do it in full generality. But now we are not interested in the scalar field by itself. We are interested in fluctuation of the scalar of my scalar quantity. Let's say my inflaton field. So the fluctuations are defined to be delta f equal to f of x mu, let's say, minus f0, the background, which in our problem will be only a function of x0, of time, because we are dealing with cosmology, so we only take the time thing. So the question is, now, suppose that I make a coordinate transformation. How the new observer that measure quantity in measuring with labels x tilde, will the fluctuation be the same as the other observer or not? The answer is no, by this simple computation. Let's say that what is delta f tilde? Delta f tilde is f tilde in x tilde minus f0, the background, which is always the same, but in x tilde 0. By definition, this is a scalar field. So the first term, I can write it down as f of x mu, because I'm using this property, minus, what is it? f0 of, now I do a transformation which is infinitesimal, so I say that x tilde 0 is x0 plus delta x0, some small fluctuation, so it will be x0 plus delta x0. Okay? Now this is equal to f of x mu minus f0 computed in x0 minus f0 dot times delta x0, because I do an expansion in linear, in Taylor, only linear. But now this term, I'm sorry if I'm lacking space, let me go here. This is nothing else than delta f minus f dot 0 times delta x0. So delta f tilde will be delta f minus a quantity. So you see, the fluctuation is not independent of the coordinate, is not gauge independent. And for my scalar field, the inflaton field, since phi dot is not 0, because otherwise inflation will never stop, I have this term. Okay, only when the background does not depend on time, the quantity will be gauge invariant. But in our case, it's not. So you can see that, suppose now that I have a scalar field, delta phi will transform as delta phi minus phi dot 0 times delta x0. Okay? And now it's clear that I can always go to a coordinate system such that delta x0 in any point is equal to delta phi divided by phi dot 0. And this, in the new coordinate system, delta phi will be 0. So it's clear that any computation that I do for delta phi does not make any sense, because I can choose a coordinate system where the result is 0, or anything I like, okay, even a constant or whatever, crazy numbers, pi square over 12 or whatever. So it is clear that the quantity is not gauge invariant. So how do I proceed now? So I have two choices. The first choice is to say, well, I have to construct a purely gauge invariant quantity to be sure that if I do a coordinate transformation, I don't pay this price. It will remain constant. It will remain independent of the coordinate choice. Or the other choice is that, of course, I fix a gauge, I fix a coordinate system, I proceed with this choice, and then I have to be sure that, of course, the result is correct. If I do mistakes along the way, I cannot check it, that if the result makes physical sense or not, because I don't know the gauge invariant corresponding quantity, you see. So what I want to do now, I want to construct a gauge invariant quantity out of which, whatever computation I will do, I will be sure that if I change my coordinate system, I don't run into a problem. Okay, so far, I have told you something that is gauge dependent. So how you, of course, there are many ways to construct a gauge invariant quantity. And I will do one way, of course, and that will take care of this diagram here. I will define a gauge invariant quantity in such a way that the delta phi will mix with the metric, and a quantity will be automatically gauge invariant. So let's do it. And I will give you the definition of a real and fundamental quantity in cosmology and cosmological perturbations that you should remember. Okay, so now we have seen the transformation of a scalar field like this. Now I want to see how the scalars inside the metric transforms. Okay, and there again I have the textbook way. Well, you know how the tensor, a covariant tensor of weight 2 transform, blah blah. You make a coordinate transformation. You have all the indices contracted. Is a mess. Okay. What I want to do now, I want to use the fact that, in fact, I know how the degrees of freedom in the metric transform, because I can use the fact that if I change my coordinate system from x mu to x tilde mu, I know that ds tilde square has to be equal to ds square, because ds square is a scalar. Okay? So let's take, for instance, let me take these degrees of freedom, this psi. How does it transform if I make a coordinate transformation? Well, using this property, what I can do, I can say that a square computed in x0 times 1 minus 2 psi is equal to the a square computed in x tilde 0, okay, times 1 minus 2 psi tilde. I want to see how this psi tilde is related to the psi. Okay. Of course, as I said, you can repeat the computation using transformation of a tensor, and you will get the same result. So trust me that this is correct. Okay. So what I do now, I do this. I do x tilde 0 as I did before, x0 plus delta x0. Okay. So now I get a square of x0 plus twice a dot times delta x0 from the first piece, and then I have 1 minus 2 psi tilde. Okay? So from here, what I do, I collect an a square, 1 plus 2. A dot divided by a is h, delta x0, times 1 minus 2 psi tilde, sorry. Okay, so from here, when you combine the two, you will see, because this now is a function of x0, you see that psi tilde is nothing else than psi plus h delta x0. Okay? So psi tilde also, so psi, the gravitational potential, so the scalar that is in front of the special part, transforms like this. Okay? It's not invariant, as you expect, and it transforms like this. You can also transform the phi, if you like, the other degrees of freedom, but for the time being, we are not interested in it. We're only interested in the gravitational potential. Okay? So now, now I'm done, because I have two quantities that transforms, and of course I can combine them to construct a gauge invariant quantity, which is called zeta, and is called the curvature perturbation, and I will explain to you why. So I define a quantity zeta, which is equal to psi plus h, and here let me put another scalar, not the phi, but just the perturbation of the energy density. I do like this. Okay? This is called the comoving curvature perturbation. Okay? And I want to show you now that is gauge invariant. And the obvious, it's because I have zeta in the new coordinate system, zeta tilde, it's psi tilde plus h delta rho tilde divided by rho dot 0, okay? But this is nothing else than psi plus h delta x0 plus h over rho dot 0 times, since this is scalar, so we transform like delta rho minus rho dot 0 times delta x0. And you see that these terms cancel this, and this is equal to psi plus h delta rho divided by rho dot 0, which is our zeta we started from. Okay? So the zeta, this quantity, is gauge invariant. So if I am able to compute the power spectrum of it, it will be just simply, it won't depend on the coordinate system. And it's related to either to the energy density fluctuations or to the fluctuation of the metric. Why it's called the comoving curvature perturbation? Because now, since it is gauge invariant, it is clear that this quantity, I can compute it in any gauge. And I will always get the same result if I have done the computation properly. So let's compute this zeta in the gauge in which delta rho is always 0, which is called the uniform energy density gauge. Okay? Zeta in a gauge in which delta rho is always 0 in any point, it will be equal to psi. Psi, but I have to remember that is in this gauge, so I put also a label delta rho equals 0. Okay? So the comoving curvature perturbation in the gauge in which delta rho is 0 is nothing else than the gravitational potential in that gauge. Okay? And why it's called the comoving curvature perturbation? Because if you compute, if you take your metric like this, if you take this metric here, and if you compute the three-dimensional Ricci scalar of your metric, this is proportional to the Laplacian of psi. Okay, so this zeta has the meaning of the. It tells you how much your space-time is locally curved. Okay, so that's the reason why it's called the curvature perturbation. On the other side, I can also choose a gauge where not the delta rho, but the psi is equal to 0, because I am free to do it. So what happens? You see the zeta computed in the gauge in which psi is identically 0, which is called the flat gauge. It's called flat because, of course, if you're thinking about this relation, the curvature of my space-time is Laplacian of psi. If psi is 0, this is 0. So locally, my space-time is flat. So in this case, I have simply h delta rho over rho dot. So my zeta is the fluctuation of the energy density. So in this gauge, you see, you start seeing that, suppose now I want to connect inflation to observables. Observable means, for instance, the CMB anisotropy, the fluctuation of the energy density of photons, which is fluctuation of the temperature. So you see now, if I use delta rho over rho to be the radiation fluctuation, it will be directly connected, so late in the universe, when the CMB is created, when there are photons around, it will be directly related to the curvature perturbation that I've generated during inflation. Okay? So that is the trick. Gauge invariant quantity, good quantity to characterize the power spectrum, and the physical meaning is the one that I just told you. Of course, during the lectures later on today, we will connect really this quantity to the observations, but for the time being, let's just use the definitions and have an intuitive relation to the quantity that we can measure, in fact. Okay, so having said that, let me compute the power spectrum of this quantity here. Okay. Again, if you have time enough, okay, what you can do. You see, this zeta mixes the metric to the real fluctuation. In fact, let me show you that in zero roll, I want to show you now that in zero roll, this quantity zeta coincides with another quantity which is called R, which is gauge invariant, the psi plus h delta phi, so my scalar field, divided by phi dot 0. I want to see that in zero roll this is true. That's the reason why I could use the R instead of the zeta, but I prefer the zeta because it's connected to observation. But during inflation, the two of them coincides. Okay, let me show you that this is true. It's not true in general, but it is true in zero roll, which is good enough for us for these lectures. Why? Because, of course, what is zeta? Is psi plus h delta rho over rho dot 0. Okay, now remember that rho dot 0 is 3h rho plus p. But for an inflaton field, rho plus p, if you remember, was just phi dot square. So this is nothing than 3h times phi dot 0 square. Okay, so now I replace here, I have psi plus h. Delta rho is what? Delta rho is the fluctuation of my energy density, but during inflation, the energy density is dominated by the potential. So what I have here, I have V primes times delta phi. And then I have divided by rho dot, which is 3h, phi dot 0 square. Okay? But what is V prime? If you remember under zero roll, I know that the equation is 3h phi dot 0 equal to minus V prime. So V prime, I can replace it by this. The 3 will cancel the 3 here. Okay, and the h will be gone. So I have exactly this quantity here. You see? So in fact, there is a minus sign here. That's the reason why. Okay, there is a minus sign. Okay, that will cancel this minus sign here. So you get exactly this quantity here. So during zero roll, I can compute either zeta or R. Both of them are gauge invariant quantities by construction, and they are in fact the same. So for the time being, I will just focus on zeta, so delta rho over rho, but I could have used delta phi over phi dot. It's the same thing. Okay. Right, so I was about to say that now we have to compute the power spectrum of this quantity zeta, which mixes the metric perturbation with the scalar perturbation, the delta phi, or the delta rho. How can I do it? You have two ways again. Either you have a lot of time, you write down your action for the scalar field plus the Ricci scalar, the Einstein-Hilbert action. You do a lot of change of coordinates, similar to the one I did for the scalar field, but a little bit more complicated, because now you have to take into account the epsilon, all the parameters, and so on. And you write down an action for the zeta. People have done it. It's a very nice computation, but of course I don't have time to do it today, because it will take a little bit of maybe a couple of hours if you identify the transformation that you have to do. So what I can do for you, maybe after the break, I can compute the power spectrum of this quantity that you already have understood it's related to something that I can observe by this identification using a gauge. Okay, so I will choose a gauge. Since this quantity is gauge invariant, I will be smart enough to choose the smartest gauge in such a way to compute the power spectrum in one line without doing any computation, using what we have learned so far. Okay, but that I will do after the break maybe. So because they are getting tired. Okay, thanks. Bye.